A vessel longer than a football field sails out into the open ocean, plants 4 steel legs on the seafloor, and lifts its entire 27,000-ton body straight out of the water. It stands there motionless while waves crash beneath it, completely unaffected by the sea. This is not special effects. This is a real ship, built for one purpose: to hoist wind turbine components so massive that no other crane vessel on the planet can safely handle them. Towers as tall as 60-story buildings, blades longer than a football field. A crane capable of lifting 1,800 tons, nearly 200 meters above the water. By the end of this video, you'll know exactly how this machine works and why a single one of these turbines can power 55,000 homes. For years, the offshore wind industry chased one simple idea. Bigger turbines mean more electricity from fewer machines, fewer foundations, and fewer expensive trips out to sea. But there was an invisible ceiling nobody could break through. It had nothing to do with the turbines themselves. It had everything to do with the ships trying to lift them.
Once turbine components crossed roughly 18 megawatts of power, they became too heavy for conventional lifting vessels to handle without risking a catastrophic tip-over. A crane swinging hundreds of tons out over open water shifts a ship's entire center of gravity, and a poorly timed wave can turn that shift into a disaster. So engineers in Europe and the United States quietly agreed 18 megawatts was the limit. Nobody dared push further because the ships simply weren't built for it. Then, China unveiled a turbine nearly 50% more powerful than that ceiling, and the offshore wind world took notice. But building the turbine turned out to be the easier half of the problem. Actually installing it hundreds of kilometers from shore in open water was a completely different challenge. That challenge produced one of the strangest-looking ships ever constructed. Delivered in August 2024 out of Qingdao, the vessel is called the Gang Hangping 5, 135 meters long and 50 meters wide, roughly the footprint of a city block. From a distance, it looks like an ordinary heavy lift ship, but hidden along its sides are 4 enormous steel legs.
When the vessel reaches its worksite, those legs punch straight down through the water to the ocean floor. Hydraulic systems then push the entire hull upward, lifting a 27,000-ton vessel clean out of the sea, like a platform rising on stilts. Once it's elevated, the ship stops behaving like a ship at all. Waves roll harmlessly beneath the hull, while the deck stays perfectly still, no matter how rough conditions get. Engineers call this transformation jacking up, and it turns a floating vessel into what is essentially a temporary steel island. That stability matters enormously, because cranes lifting 1,000-ton loads 200 meters into the air cannot tolerate even a few centimeters of deck movement. At that height, a small wobble at sea level becomes a wild swing at the top of the crane arm. But here's where things get interesting, because pushing 4 massive legs into the seafloor is far riskier than it sounds. The ocean floor often looks solid from above, but hides a thin crust of packed sand sitting over loose mud, silt, or trapped pockets of water.
If a leg punches through that crust unevenly, it can suddenly sink several meters in seconds, a phenomenon the offshore industry actually has a name for: leg punch-through. It has caused real accidents on support vessels worldwide, some severe enough to force emergency evacuations. So before the Gang Hangping 5 ever lowers its legs, a survey team scans the seafloor with sonar and drills physical test samples to map exactly what lies beneath. Then, as the legs descend, onboard sensors track the pressure under each one in real time. If a single leg starts sinking faster than the others, hydraulic pumps instantly correct it, keeping the whole platform level before a human would even notice a problem. Once the ship is locked in place, the real spectacle begins, lifting one of the heaviest single objects ever installed in open ocean. The turbines involved come from the Chinese manufacturer Dongfang Electric, and their scale is difficult to picture. The hub alone sits 185 meters above the waterline, taller than most skyscrapers. The 3 blades sweep a circle 310 meters wide, an area covering roughly 10 football fields.
One of these turbines can generate around 100 million kilowatt hours of electricity annually, enough for 55,000 homes, while offsetting about 30,000 tons of coal. That single machine now does the work that once required a dozen smaller turbines, meaning fewer foundations drilled into the seafloor and fewer costly voyages to install them, which is exactly why engineers were determined to break past that 18 megawatt ceiling in the first place. To set the generator assembly onto the tower, the crane must hoist close to 1,800 tons nearly 200 meters into the air, suspended above open water the entire time. At that height, even a modest gust of wind puts enormous stress on the crane structure. And there's a problem most people would never think to consider: sunlight. When sunlight heats one side of a 200-meter steel tower more than the other, the metal expands unevenly, and the top of the tower can drift off-center by several centimeters. On past offshore projects, that alone has forced entire crews to halt work and wait for nightfall before continuing. On board the Gonghanping 5, computers continuously track sunlight, temperature, and wind speed, adjusting the crane's alignment automatically, so these invisible shifts never cause delays.
This is where the ship's most impressive engineering trick comes into play, because logically, swinging a 1,000-ton load out to one side of a vessel should tip it over, the same way leaning too far off a rowboat capsizes it. The solution is called active ballast control. Hidden inside the hull are massive tanks that fill or empty with seawater within seconds. The instant the crane shifts weight to one side, pumps move hundreds of tons of water to the opposite side, canceling out the tilt before it becomes noticeable. And because the crane can swing a heavy load in just a few seconds, the ballast system doesn't just react, it predicts. The onboard software calculates the load shift based on the crane's planned movement and starts correcting before the tilt even begins. All of this, the seafloor monitoring, the ballast adjustments, the thermal tracking of the tower, produces more data every second than any human crew could process manually. That's why the entire ship runs on what engineers call an intelligent control platform, a single system managing ballast, positioning, and crane operations together instead of as separate parts.
It continuously reads real-world conditions like wind and water density and adjusts automatically, cutting fuel consumption by roughly 20% compared to ships without this kind of automation. For a vessel that spends extended stretches at sea moving between turbine sites, that fuel savings adds up fast. Naturally, a system this critical needs backup. The Ganghanping 5 runs 3 separate positioning systems simultaneously: China's Beidou satellite network, GPS, and laser-based sensors. So if one fails, the others take over instantly. Its navigation and crane computers operate on a closed network with no connection to the public internet, making outside interference essentially impossible by design. This layered redundancy mirrors the kind of fail-safes used in aviation and spaceflight, where a single point of failure simply isn't acceptable. And if something does go wrong despite all of it, the captain can turn one physical key to shut down every automated system instantly and switch to full manual hydraulic control. Even with all that engineering, one opponent still pushes this ship to its absolute limit: the super typhoon. The South China Sea produces some of the most violent storms on Earth, and offshore wind farms in the region have suffered real damage from them.
Typhoon Yagi in September 2024 tore into older turbines nearby and showed exactly how destructive these storms can be. So when a typhoon approaches a turbine installed by this ship, an automatic sequence kicks in without any human input. The blades rotate edge first into the wind, drastically cutting the resistance they present to the storm. Meanwhile, the ship raises its hull even higher on its hydraulic legs, letting dangerous waves pass harmlessly beneath the deck instead of slamming into it. Once the storm clears, the same automated systems bring everything back online, and the turbine resumes generating power almost immediately, without days of manual inspection or repair. From a hull that lifts itself clear of the ocean, to a crane hoisting skyscraper-sized components through open air, to a turbine engineered to shrug off a super typhoon, this project is a reminder of what happens when engineers refuse to accept that something is simply too big to build. What part of this surprised you the most?
Let us know in the comments. And if engineering on this scale fascinates you, like this video and subscribe so you don't miss the next deep dive.